Welcome everyone to part 3 of Math and Measurements. We got a few or a couple of objectives here. Let's go through them. Determine the number of significant figures in a given number and a number that is the result of a math calculation. Express numbers and perform calculations in exponential notation, and one more, round off numbers to the desired digit. So let's go ahead and jump right into this here. So let's talk about rules for significant figures here. For math operations, right? So for the first operation, let's talk about multiplication and division here. So in order to do a math operation with multiplication, the number with the least amount of significant figures is going to be the least accurate number. So 1.4 is less accurate than 4.56. So if 1.4 is less accurate, my question mark cannot be more accurate than 1.4. Since 1.4 limits my accuracy, my answer must be limited to two significant figures. I hope that made sense. If not, rewind, listen to it again. So we need two significant figures, right? Because two significant figures here and three significant figures there. Right? I'll just put SF for significant figures. So our answer must have two significant figures. So let's see how we do this. So we're going to get 6.38. We're going to round that to two significant figures. We look at the 3 here. So here's my second significant figure. Take a look at the number next to it. If it's greater than 5, you're going to round the 3 up. And 8 is greater than 5, so we're going to round the 3 up to 6.4. So here it is. The same thing goes for division. Okay, your answer is going to have the least number of significant figures there. So for addition and subtraction, a little bit different. The result should have the same number of decimal places, right, as a measurement with the fewest number of decimal places that was given. So for example, if we have two numbers or two measurements, right, again, these are simplified, no units, just so we can concentrate on the numbers here. But imagine that they do have units, whatever they might be. So here we have addition, and we're going to add three numbers, each with different or varied amounts of decimal places. This one here, 12.11, has two significant figures past the decimal place. Here we have one significant figure, and here we have three significant figures. Again, we're only counting or looking at the decimal places. The one with the fewest number of decimal places is going to, again, limit the accuracy of the measurement. So in other words, limit the accuracy of this answer here. So which is the one with the least number of significant figures? That would be this one. I'm limited to one significant figure. So we're going to line these up, to add them up. We get 31.123. The fewest number of decimal places is 1, so our answer is going to be 31.1. How did I get 31.1? We'll look at the 2 next to it, right? The 2 that's less than 5, so this stays as 1. So let's take a look at rounding a little bit closer. So if the digit to the right of the last significant figure is less than 5, remove that digit. Okay, and I'm talking about the digit to the right of the last significant figure. So in the last example, it would have been 1, right? 1 is the last significant digit. Why? Because, again, that's as accurate as we can be here. Go ahead and round using the number next to the last significant digit. So round 4.348 to two significant figures. So we're going to take a look at two significant figures here. This is my first and second significant figure. So we need these two. Let's take a look here. 4 is less than 5, so we're going to keep 4.3. Right? We're just going to remove the 4 and the 8 there. So exceptions to significant figures, right? PH, exceptions to the rule. Only the decimal places are significant. So in other words, how many significant figures are in the measurement? PH equals 10.9. 1. Right? There's one significant figure here. There it is. We're only looking past the decimal place. So let's take a look at exponents. Exponents, really large or really small numbers, are written in exponential notation. It usually looks like this. Number, and we put it as a times 10 to the power of n, right? However many times you need to move the decimal place to the left or to the right of this coefficient in the front. So in exponential notation, only the coefficient is significant and not the exponent. So in other words, the times 10 part is not important when deciding if it's a significant digit or not. So when you calculate with exponents, there's a shortcut. Here we have an example, 10 to the power of a times 10 to the power of b. How do we figure out that answer? Well, we can just add these two exponents when we have a multiplication of scientific notation. We can just add the exponents to give us a rough estimate of what our answer should come out to be. For division, you're going to subtract your exponents to give you a rough estimate of what your answer should be. For addition and subtraction, sorry, there's no shortcut. You got to either plug it into your calculator or do it by longhand. Negative exponents, remember, 10 to the negative 4 actually means 1 over 10 to the 4. So again, that negative means that it's an inverse number there. You can use this actually as a conversion factor. You can use it as 10 to the 4 over 1. Okay, depending on what units you need to cancel. Express this number, 26 million, in exponential notation. So how are we going to do that? Well, let's start here. To make this a number between 1 and 10, we got to move this decimal between the 2 and the 6. And there it is. To get our original number back, we have to move it 7 spaces to the right, which gives us 2.6 times 10 to the positive 7. In other words, so one more time, to get our original number back, we got to move our decimal where we placed it 1, 2, 3, 4, 5, 6, 7 spaces to the right. Another example, express 0.00055 in exponential notation. One more time, let's make this a number between 1 and 10. The way to do that is we're going to take this decimal and move it between the 5 and the 5. So now it is a number between 1 and 10, 5.5. From this location, how many places do I need to move this decimal to get my original number of 0.0005 back? Well, we got to move it 1, 2, 3, 4, 5 places to the left. So that means that it's 5.5 times 10 to the negative 5, since we got to move it back to get our original number. Here's another example. Estimate the answer. So how do we estimate this answer here, right? Say you don't have a calculator and you need to do this calculation in your head. And these problems do come up occasionally on multiple choice sections where you're not allowed to use your calculator. So if we take a look, 3.4 times 10 to the positive 5 times 2.3 times 10 to the positive third. Well, since we're multiplying exponents here, we can simply add, right? We're going to use our rule of addition for these two products here. So our answer, 5 plus 3, is going to come out to something times 10 to the positive 8. Now if you look at our two numbers here, 3 times 2 is 6. Now we got a little bit more than 3, a little bit more than 2. So our final answer is going to be some number a little bit higher than 6 times 10 to the positive 8. Did you see how I was able to estimate that? Right, so it's going to be something approximately 6, again, approximately 6 times 10 to the positive 8. Okay, and that's it. Part 4.